Ladies and gentlemen, welcome to the second part of our beam tutorial. We are now ready to input the pre-stress. So let's navigate to Tendon Design in the top ribbon. A new window will open, and there in the menu on the left side we can find the tendons layout. And now finally the correct table appears at the bottom of the screen. In this table, we can define the tendon groups. And what are they? In our case, each tendon group will represent a row of tendons in the cross-section. After that, we can define pre-stressing steel class for each row, and we can also define the pre-stressing force or the initial stress in the tendons. After inputting these values, the application will check whether the inputted pre-stressing force doesn't exceed the limit which is defined in the code. When it does exceed the limit, we get a warning. In our case, it doesn't exceed, we get a green check mark. If we click on Material, it's possible to adjust the mechanical properties of the material, which can be useful, for instance, when dealing with an older structure. One of the properties defined here is also the relaxation class. So let's now talk about the relaxation. Relaxation describes the time-dependent relaxation of stresses at constant strain. While prestressing essentially represents an applied strain state for the prestressing steel, this inevitably leads to prestress losses. This is described in Annex D of Eurocode 2. A crucial factor for capturing prestressing steel relaxation is the relaxation coefficient, which is needed to calculate relaxation losses. In Eurocode 2, we find three relaxation classes which are taken into account in the beam application. Usually, class 2 is used for newer prestressing steels, while class 1 is used for older prestressing steels that are already in the existing structure. It's also worth mentioning that maintaining constant initial stress for a period of time can significantly reduce the value of prestress losses due to relaxation. Before we can carry out the calculation of prestressing losses, we need to click on Design Members and to look at the initial values for calculating the prestressing losses. Our example refers to the stressing bed method. You can see it pictured on the right side. In this case, the strands are tangent against the abutment. Then the precast elements are concreted, and after the concrete has hardened, the anchorage is released and the prestressing force is transferred to the member. Since the strands are usually arranged eccentrically, this process leads to negative bending. Now, there's a question, how stiff are actually these abutments? Often they are not infinitely stiff, so in this case we need to enter a displacement. For example, we can enter a shortening of the prestressing bed of 1 millimeter. This will lead to prestressing losses. Of course, we can ask the precast manufacturer which value is representative. We can also enter an anchorage slip, and we can select if the release of the prestressing force is gradual or sudden. This input affects the transmission length. We can also take into account the prestress loss, which happens due to the difference in temperature between the concrete and the tendons. And the last thing we need to define is the so-called short-term relaxation. This is the relaxation that happened before releasing of pre-stress, and we have two options how to consider this. The first one is so-called by the time, and this is described in NXD. It is the detailed calculation method. Stress intervals are calculated and summed, and as input values we take the time of a constant initial stress, which we assume to be 30 seconds in this case, and then the duration of the short-term relaxation. In this case we consider 16 hours. It's also important to note that we can take into account the influence the temperature has on relaxation. There's a method how to do it described in the Eurocode. We need to calculate the effective or equivalent time according to this formula and input it here as a duration of short-term relaxation. The second option is called defining of percentage. This is much simpler. It means we just input the percentage of relaxation. We can usually find this value in the technical approval of the prestressing system. Usually this value is somewhere between 1% or 1.5. I already mentioned the loss due to the difference in temperature between the concrete and the tendons, and on this slide you can see how this is taken into account. There's a formula in the Eurocode that's considered in the beam application. Basically, you can see the heat curing of concrete has its advantages, but it can lead to prestressing losses. Okay, we have entered the initial values, and now we can enter the strengths themselves. And the strengths are entered relative to the edges of the cross section. Here it's the edge 4. We define the number, the covers, and we can also define a blanketed length. This is the length where there is no bond between the tendon and the concrete. These values can be defined separately for each tendon group. We can click cross-section at the top ribbon and see how the tendons are arranged. There is also an option to display a 3D representation of the geometry. This is particularly useful when there are parabolic tendons in the structure. Let's now take a quick look at prestressing losses. We distinguish between short-term losses that occur immediately after prestressing and long-term losses, which develop over time. Short-term losses arise from different mechanisms. They can be the elastic compression of the concrete, where the elastic modulus plays an important role. Then there are losses due to the deformation of the prestressing bed. We have the losses due to anchor slip, as specified in the technical approval of the prestressing system. And there are also frictional losses due to the geometry of the tendon and the short-term relaxation as well. Long-term losses, on the other hand, they are usually caused by creep, shrinkage, and the long-term relaxation. Of course, whether it is short-term or long-term losses, time plays a crucial role here. Therefore, it is always important to make realistic assumptions about the construction stages. When discussing time, we often think of creep and shrinkage, but we sometimes tend to forget that the time evolution of compressive strength and elastic modulus plays an important role as well. So this slide shows the evolution of the elastic modulus and compressive strength of concrete over time. And Beam takes these parameters into account in its analysis. We can calculate both the short-term losses and the long-term losses in Beam. And the results are represented both graphically and in a table. We can see there's the initial stress, there is the stress after the short-term losses, and with the blue line we see the stress after the long-term losses. It's advisable to always check these results, and if there are big differences between the stresses, there may be a mistake in the definition of prestressing. The transfer of forces via the bond requires a certain length at the end of the beam. And on this slide, you can see how this transmission length is calculated in Beam. It's done according to the Eurocode. You can see here that the gradual or sudden release plays a role here, or the good bond conditions and some other coefficients as well. Let's now summarize the tendon input in a short video. Here we click the tendon design and a new window opens. At first we see the construction stages as we had defined them previously, and upon clicking on design members we can define the parameters of our prestressing method. Here are the abutment deformations and so on. The tendon layout itself is defined here. You can see five tendon groups. We can add a new one. We can name it as we like. We can change the initial stress. And as you can see, when it's over the limit, we get a warning. We can check the geometry in this 3D representation. And we can edit the parameters of tendon groups here at the bottom. This can be done separately for each prestressing group, as you can see. Now let's delete this one. And let's continue to the results. We now click to calculate, and let's wait a few seconds for the results. Okay, the results are here, and we can see the stresses, and we can take a look at prestressing losses too. What I forgot to mention is, of course, we can change the material if we like to. Here are the prestressing losses. Then, as you can see, we can see the initial stress, the stresses after short-term losses, and the stresses after long-term losses, blue line, graphically or in a table below. Here we can check the internal forces, compare them to what we expect, do a check. We can copy these pictures to clipboard, use them in our report or anywhere we want to, and there's also a possibility to generate a report. This one is the detailed one. As you can see, there is all the information we need included in this report. So we can exit now. Once we are satisfied with the tendon layout, we can click Calculate and we get the results. The first step should be to check the support forces, because we should always do a plausibility check. And if the support forces are not as we expected, it indicates that the loads were probably entered incorrectly. We can see the results for each of the construction stage here. The same applies to the internal forces. We receive internal forces for all relevant load case combinations. And are the internal forces possible? We should always check this. And if not, maybe some of the input is incorrect and we should check it. So if we are sure that our system has been entered correctly, we can move on and we can now deal with the concrete design. If our system is not subject to torsion, we can switch off the torsion and interaction checks. The detailing check is related to the code provisions. This should always be checked by the structural engineer. And on the right side, let's not forget to enter the exposure classes correctly. Here we can see a few excerpts from the Eurocode. Please always check in the Beam application whether the correct width and the corresponding load combination are correctly taken into account. The reinforcement bars can be entered very precisely in Beam. We click on reinforcement, and at first we enter the reinforcement zones. This way we can enter the amount of reinforcement present at each point along the system. For common cases, we can work with reinforcement templates, and this way we can input the reinforcement very quickly and then just adjust the diameters. We can enter the longitudinal reinforcement and the stirrups as well. Here we show a short video how the reinforcement can be defined. We just click reinforcement. These are our two reinforcement zones as we defined them. And now we can edit the reinforcement. At the top ribbon, there's the option to input a template. And here we can just adjust the parameters. And when we click OK, the reinforcement is there. As you can see, the covers are applied according to this table. There are two stirrups defined and the longitudinal reinforcement. We can adjust every value. We can explode the layers, or we can add new layers here. As you can see, now we have new layer. We can change the diameter. We can change the position. Now it's user defined, and we can define the covers as we wish. So we can move the reinforcement upwards this way. There are also coordinates as another possibility how to input the reinforcement. So we have defined the reinforcement, we have defined the tendons. So we can now start the calculation and analyze the results. Beam provides us with the utilization factors for each construction stage. And based on these, we can identify the relevant checks and act accordingly. Whether it's the ultimate limit state or the serviceability limit state, the beam gives us this information and we can check what went wrong. This slide shows the summary of the utilization factors, which allows us to see where the decisive check is. As already mentioned, we can obtain and view the results for each individual construction stage, both graphically and in tabular form. Here are some more results. The utilization factors for the design with bending moment and longitudinal force are shown here. This includes, for example, the stages of prestressing, intermediate storage, and final state. The utilization factors for the check of stress limitation are also presented here. This slide shows us the utilization factors for the shear capacity and the decompression. We can see the problems here. The shear capacity is exceeded. There is more than 115% of utilization, and the 1000 value by the decompression check indicates that the check has not been successfully carried out. In such a case, we should check the shear reinforcement and tendon geometry, check it, adjust it, try to find a solution. If we find any exceedance of load-bearing capacity and we want to find out where they come from, we can click on the Detailed button, and this will give us a list of the utilizations for each construction stage at each location. We can then select the results we are interested in and click on Results. On this slide, we get the detailed information about the shear resistance checks. And here we can see the values of resistance of the compression strut, the resistance without reinforcement, the inclination angle of the compression strut, the static height, and so on. So this allows us to understand how the beam application performed those calculations. By default, the inclination of the compression strut is 45 degrees, but we can change this value. So at the right bottom corner, you can see how the results change when we change the value from 45 degrees to 40. So this way we dealt with the shear problem. But what remains is the problem with the compression. Here you can see the crack width check for the section 8 near the middle of the span at the end of a design working life. And the picture, you can see that the tendons are in the tangent area, and that's where the problem is. It's good to remember how the stress limitation check works. So here we have an extract from the code regarding the stress analysis. Beam takes the national annex into account. We selected the German national annex. So as you can see, here are the coefficients as defined by the German national annex. For the prestressing force, a certain degree of variations has to be taken into account. Those are the coefficients R sub and R inf. They cover the uncertainties in the prestressing force resulting from the uncertain prediction of friction and time-dependent losses and so on. In case of pre-tensioning, smaller variations can be taken into account. As you can see, the factors Rinf and Rsub may even be set to 1, but only if appropriate measures are taken, e.g. direct measurements of pretensioning. Beam calculates the correct width taking into account the reinforcing steel strains in state 2, meaning the correct cross-section, and the tensile stiffening of the concrete between the cracks. The corresponding formulas can be found in section 734 of Eurocode 2. A frequently asked question is whether the maximum crack width can be changed. Some colleagues may prefer values of 0.15 or 0.10 in some projects. And yes, this can be done. To adjust this, we can click on Code, then navigate to WMax in Chapter 7 and see the table with the correct width according to Eurocode 2. Here we have the option to enter our own value. Here a short video with a summary of results. When we click on results, we get the summary. We can adjust the display options. We can choose which extremes will be described as well. And we can display the desired construction stage, or we can show all of them. There are many checks, the capacity in combination, then we can see here the shear check when we can display all the values, and then the stress limitation check again for concrete, tendons, reinforcement, and here we can find the correct width check. There's option to create a report, and we can also check the results in more detail here. In this window, we can select the section which is of interest to us. We can select the construction stage we are interested in, and then this is the cross section, and then we can display the results. We get the overall results, which are listed here, and then we can check in more detail the capacity of combination of normal force and bending moments. Then there is the shear check, again with all the results here in the table. And here's another option, how to check the inclination of the strut. The stress limitation is again displayed here. There are many options. The display can be adjusted. We can see it in 3D or 2D. And similarly, it's also the case with the correct width. Here we can see the stresses in reinforcement and concrete and tendons as well. We can again copy these pictures to clipboard, use them in our report, and so on. You may have noticed on the previous slide that we already complied with the decompression check. That's because I optimized the tendons. I increased the initial stress in tendons, as you can see, and I also adjusted the setting of the prestressing bed. You can see the new settings as well here. This has some influence on shear additionally, but in our case we can say that the utilization of 100.5 is okay. If the compression in concrete is exceeded, we may have to input a higher grade of concrete, or we have to change the dimensions of the cross-section. Both of these options are quite unpleasant, and they increase the cost of the structure. There are some possibilities to optimize the structure in Beam, and the first one is we can include the calculation of nonlinear creep in case the stress limit for the quasi-permanent load combination is exceeded. Some national annexes may provide room for optimization in the case of the characteristic load. For instance, the German annex permits that the factor for compression and characteristic load combination is increased by 5% in case the sufficient confinement is ensured. Let's now proceed to the stability check. The lateral deflection has to be taken into account in some cases, mostly in case of slender beams with pre-stress. We have two options how to do this in the beam application: the simplified check or the advanced calculation. The Eurocode defines conditions under which the second-order effects can be ignored. This is done by the so-called simplified check in the beam. We just input the required parameters. Here the length of the compression flange between the lateral supports is of particular importance, and we get a result. In our case, it's a green check mark, meaning that the second order effects can indeed be ignored. In addition to this simplified check, we can perform a sophisticated materially and geometrically nonlinear analysis to determine the design internal forces for several design situations. It's lifting, transport, the final supports, and the end of design life. However, this type of analysis requires a significant amount of input. So let's now take a look at how this is done. At first, we have to change the type of the project to be able to input the load in its real position with correct eccentricities, because whether the line load acts at the top or at the bottom of the cross-section has a different stabilizing or destabilizing effect on the beam. There are two design situations dedicated to lifting, which are identical in terms of inputs and calculations. The user has a choice of two lifting methods: inclined slings or vertical slings. For both, it is possible to set the length of lifting eye, which controls the vertical distance of the lifting point, means the center of rotation, from the top surface of the beam. The lifting point is the point at which the flexible support joins the rigid body. A line passing through the lifting point at each support forms a roll axis. Horizontal distances can also be set using lateral eccentricity and distance from end. Both lifting points can be set independently, it means asymmetrically, so it is possible that the roll axis will not be parallel to the beam axis. For inclined slings, it is also necessary to specify the height of the crane hook used to define the lifting angles, and the additional normal force from the sling. We can also select how the initial geometric imperfections will be considered, whether it will be done automatically by code, or alternatively we can input our own value. Then there is the transport design situation. This is probably the most complicated one. The beam is transported in such a way that one end of it lies on the truck and the other on the trailer. In terms of calculation, this means that one side, the truck side, is supported by a perfect hinge, free to roll, and the other side, the trailer side, is supported by a hinge with a defined rotational stiffness. As for the truck, of course, you can enter the position of the truck to define the distance from the end of the beam. In addition, you can also specify the bearing height, which is the vertical distance of the roll axis from the bottom surface of the beam. And as for the trailer support is also a point support, but with a defined rotational stiffness. Position of the trailer defines the distance of the support from the end of the beam, and bearing height again defines the distance of the roll axis from the bottom surface of the beam. The rotational stiffness of the trailer support is defined by the stiffness of the axles themselves, where the total stiffness of the trailer support is the number of axles times the rotational stiffness of one axle. Recommended values for the axle stiffness can be found in literature. It's in the range of 340 to 680 kilonewton meters per radian per dual tire axle. The higher values apply to rigs without leaf springs, in which the springs is primarily in the tires. For a single axle, the half value can be taken into account. And the last input is the initial lateral tilt angle alpha. This expresses the road tilt. The standard roadway tilt is approximately 1.5 degree, with the possibility up to 5 in curves on standard roads. As for the final supports, we got 3 options. It can be elastomeric bearings, fork, or a bearing pad with a dowel. With elastomeric bearing, we need to define its geometry, its position, width of the bearing, length, and also the thickness and the stiffness of the bearing. The left and right bearing can be specified independently. As we already mentioned, it leads to the possibility of the roll axis not being parallel to the beam axis. With the fork, the bearing pad with dowel supports, in terms of the model, these two types are identical. Support is placed on the bottom of the surface of the end of the beam, which is rotationally rigid about the around the x-axis. However, it is possible to specify user-defined rotational stiffness if the user wishes to define it that way. And as for the end of design working life, the settings for the last design situation are taken from the final supports. This means that a model is calculated where only the age-dependent characteristics are different. In the combination tab, the user can define any number of combination in the same way that combinations are entered for the basic calculation. And the load cases relevant to the individual design situations are always available here. And lastly, a dynamic factor for permanent loads can be added to the combinations for lifting and transport. Here you can see a table with recommended values. As already mentioned, this is a fully materially and geometrically nonlinear analysis. It means that the reinforcement and the tendons are both taken into account, and the concrete in tension is automatically excluded from the calculation. The cross-sectional characteristics are adjusted during the calculation to take into account the actual cracking of the concrete. Then, as a result, we get the deformations and the internal forces, which can be represented both graphically and in a table. It's important to understand how this works. So let's talk about the deformations a little. At the first step, the beam is deformed into a parabolic shape using the value of the initial imperfection. Then in this shape it is mounted on hinges. This causes an initial rotation, so the center of the gravity is below the roll axis. So this is the initial deformation. And loads are then applied, including the proportional distortions from shrinkage, and nonlinear calculation is run to determine the additional rotation and deformation. So this is the increment of deformation, and as a summation of these two, we get the total deformation. At the present, we need to take these resulting internal forces and export them to the RCS module and perform a check there. In future, this will be patched so that the whole analysis can be performed here in the beam. The beam can also calculate the deflections taking into account the concrete cracking. It is a well-known fact that the maximum deflection must be below a certain limit in order not to affect the appearance or the serviceability. So when subjugated to bending stress, cracks appear in the concrete, causing concrete to go into the cracked state where the stiffness is minimal. But between the cracks, the concrete remains uncracked, and the stiffness may be twice as high. For this reason, Eurocode 2 includes a formula for calculating deflections or curvatures that represent an interpolation between the uncracked conditions and the fully cracked conditions. You can activate the deflection check in the Data tab. The StatiCa Beam application provides several calculation options and display options for the results. On this slide and on the following one, you can find an overview and an explanation of each type of the result to navigate the results correctly. There are four of them: the linear, immediate, meaning the short term, and the long-term deformations, and the total deformations. In case of linear deflections, there are several differences compared to the other three. Mainly, it is that the linear stiffness without cracks is considered, and the change of support position during construction stages can also influence results in this case. The other three types of deflections are all nonlinear, taking into account the crack development in concrete. It's important to note that all loads are applied to the resulting structural system defined in the final supports stage. So the difference lies in the stage considered and in the load combination applied, whether it's quasi-permanent or characteristic, as you can see described on the slide. The long-term deflections and the total deflections are both calculated at the end of the design life. The difference between the two of them is in the load combination. For the long-term deflection, the quasi-permanent load combination is used, and for the total deflection, the characteristic load combination is applied. In the middle of the slide, you can see the summary of deflection checks. All four values are tabulated there, and you can compare them with the limit value in the utmost right column. The last thing I want to show you is the report. You can select the standard or the detailed one. There's really not much to say. You can see there are many options on the right side. You can select what you want to display. You can can select if all construction stages will be included or only the selected ones. You can do this for the model and for the concrete design in 1D as well. There's the lateral stability, the bill of material, code settings, and so on. You can see the report is quite long. All the important inputs and results are included here. We have changed some settings, so now we have to refresh the report, and then the export to document or to PDF becomes available.